Section 1.2 will be covering functions and their graphs, and we'll kind of do the objectives in a weird order, but I put them in an order which I felt made sense. So let's first look at objective 1. We're going to determine whether correspondence or a relation is a function. So we're going to define a function and then see if things are or are not functions. So a relation is just a correspondence between a first set called the domain. So guys, this is typically your x values, okay? Do they have to be x values? No, it could be our age or something like that, right? And then a second set is the range. That's typically our y values, all right? Not always, but most of the time when we're talking about algebra. All right, so what makes a function a function? It's when whatever the relationship is, each member of the domain corresponds to exactly one y, okay? So each member of the domain corresponds to exactly one of the range, okay? So in your domain, if you have an x value of 2, it should only be going to one y value, okay? You can have y's that have multiple guys coming to it, but each x only has one y. So in other words, if a relationship is a function, then for every input, there's exactly one output. So for every input, there's exactly one output. So you can kind of think of it as a function as a machine. You input it, it goes through the machine, beep or bop or beep, and out comes one value. That would be a function. It says why? Why do we care about this? Because functions are what we use in our everyday life to predict. So you might have a function for revenue, for your paycheck, whatever it may be, and you would input how many hours you worked that week. It'd go into the function, beep or bop or beep, and out pop with your salary or whatever it may be, okay? So let's look at this kind of thing going on here. Example 1, we have 4 things to look at, and we want to know with each of these relations, are they a function, yes or no, and what's the domain and range. So we haven't really defined domain and range exactly. We're going to define that a little bit more specifically here. But in this case, we're going to just use this definition up here. The first set's domain, the second set's range, okay? And we're going to use that definition. So what is the definition of a function? You should have one x going to one y, okay? Meaning there should be one arrow coming out of each of these x's. And what do you notice? Each of these x's have one thing coming out of it. Can 9 and 36 have 2 things coming to it? Yes, we don't care about what's happening with the y's. We just care about that each x is going to one y, okay? And do you agree that negative 6 only has one y value? 36. Positive 6 only has one y value? 36, and so on. So this would be a function. So since it is, let's talk about domain, and let's talk about range. And again, we don't know the full definition, but according to the domain definition up above, it's just the values in the first set, okay? So our domain just consists of those 5 numbers. So we'll just do squiggly brackets and list those 5 numbers. Because the domains are the input, okay? And whatever function this is, which we can probably look at it and guess what function it is, we're going to put negative 6 in, goes through the function, beep or bop or beep, 36 pops out. But look, when we put positive 6, beep or bop or beep, 36 pops out. What happens when we put negative 3 and positive 3? 9 pops out. So what is our function? What do you guys see in the pattern from x to y? What are we doing to these numbers? We're not only multiplying, we're squaring them, right? Negative 6 squared is 36 and so forth. Are they asking us that? Are they asking us to define the relation? No, but that's the whole idea. You have these x values, you're going to input them into your function. In this case, it'd be x squared, and you would get those outputs. That's your range. So what are the outputs? 36, 9, and 0. Is that okay? Notice that your range and your domain don't have to have the same amount of things in it, correct? Because when you square a negative and when you square a positive, you get the same y value. So there's not as many y values in our range as there were in the domain. Let's look at this next set. Right now, it's not obvious what the first set and what the second set is, so we can make it that way. Let's write 9, 9, and 2 here, right? And then negative 5, 5, and 4 here. So I'm kind of putting this whole input of x's and matching them to their y's. And actually, I kind of did it incorrectly. Guys, can you correct yours? Sorry. I just want to make it more obvious. Why would we write 9 twice? We wouldn't, okay? So to make it obvious, we actually just write 9 once. But what do you notice about 9? What's happening to him? that one single y is going to that one single x of 9 is going to two different y's, okay? So notice we have 9, so I should just list them once. I'm sorry about that. And then the only other input we have is 2. So we're going to put him there. Is this a function, yes or no? So for every input, there's exactly one output. No. Who ruins it for us? The 9, because he goes to two different 5s. You got it. So this is no. And maybe we'll make a note. 9 has 2 outputs. So 9 is the same number. We put him in once, but what pops out? A negative 5 and 5. So that's not a function. All right, let me do a better job of doing C. What we're going to do is we're going to put all our x values to put the first set, but if a number repeats, don't write it. So we have negative 2, 5, 0, and 4, kind of as our first little set of x's. And then we have 5, 7, 1, and negative 2. That's our set of y's. And guys, this is actually just straight across, right? We have one x for every y, and one y has one x. So, since we only have one arrow coming off of each of those x values, is that a function, yes or no? Yes. Yep, every x has its own individual y. So we'll say, yes, it's a function. And since it is, guys, we can talk about domain, what were our inputs, and we talk about range, what were our outputs. All right, so your domain is just what you put in. It's your original set, negative 2, 5, 0, 4. And then your range is your outputs, what came out of each of those. 5, 7, 1, and negative 2. This one is not obvious. I don't really see a pattern there, okay? So this is one where we would probably need an equation to know what the input-output relation was. But right now we just want to note that every x goes to one y. Let's do the same thing over here. Let's write negative 5, 0, and 6 for x's, and then we have 3. Oh, that's kind of weird. And each of them go to 3. Is that a function, yes or no? Yes. It is, right? So you could first get tripped up because you're like, 3 has a lot of stuff coming to it, but we don't care about the outputs, how many things they have coming to it. We just care about those inputs. Each of those inputs goes to 1, right? Isn't there only one value that negative 5 goes to? Yeah, 3. Isn't there only one value that 0 goes to? Yeah, 3. So as long as each of those inputs have one arrow coming out of it, it is a function. So the domain, guys, would be those 3 inputs we put in. Negative 5, 0, and 6. And then our range is just that one value, 3. And this function, guys, would just be a horizontal line, right? It doesn't matter what your x's are. What is your y value is always? 3. And so our function would just be y equals 3 there, and it didn't matter what x we put in. Okay, if there's no questions there, let's just go ahead and turn the page of what's going on. So now that we can kind of see it with numbers, what does it look like graphically when it comes to functions? We're actually going to have a little trick of the trade to know whether a function is a function or not. So the key thing is to remember, for a relationship to be a function, every input x has one output y. So let's look at these graphs. So to kind of make like almost like a shallow bowl, guys, going through the origin. So looking at this, would this be a function, yes or no? Well, do you guys agree that the x-axis, as we move from left to right, are all of our x values, right? So if we look at any given x value, it doesn't matter. Let's say we want to pick this x value. What's the y value goes with it? That y value and only that y value, correct? Pick another random x. Say we're over here. What's the y value that goes with that? That y value, and that's it, right? So notice any x you pick, you just go straight up, and it's only going to hit that one y value. So is this a function, yes or no? Yeah, every x just has that one point on the graph. So this is a function. And then you're going to quickly see what happens when we turn it the other way. So make a shallow one, but off to the side this time. So turn your paper sideways. And what did you say, Riley? It's going to be a no, because you're going to see as we pick those positive x values, it's going to have 2 y's. Do you notice that? Okay, so 0's fine, but remember it's every x has to have only 1 y. So even though 0 makes the cut, what about this x value? What happens? He has this y value and that y value, right? Or if we pick this x value, he has this y value and this y value. So every x other than 0 actually has 2 outputs. So this is not a function. So how do they define what you guys noticed? Like you guys kind of found the little trick is it's called the vertical line test. As long as you pass a vertical line through every x value and it crosses your graph no more than once, then you have a function, right? So like if we could draw a vertical line through all these points, we only cross it once. Here we don't cross it any, that's fine, but here we cross it twice. So if it crosses it more than once, it's not a function. So that's all this middle part is saying. If it's possible for a vertical line to cross a graph more than once, then that graph is not a function, okay? So all you do is kind of just, like I just kind of throw them out there like this. Is that crossing the graph more than once? Those vertical lines on A? No, so that would be a function. What about this guy? Well, these are okay leading up to here, but once you have this little double back happening, do you guys see there's a couple points where we're hitting it more than once? Yeah. So that would be not a function? Or yes or no. Sorry, I'm kind of getting a little wordy here. This is kind of exactly what we drew right above, except for it shifted a little bit, right? So here we're not crossing it at all, which is fine. Here we cross it once, that's fine. But then once we get this direction, you notice each guy is going to have 2 outputs. So that's no or not a function. What about your oval on D? No, just like a circle. Yes, sir. Did you have a question?
No,
you're just stretching. Sorry, I thought you had a question. So that's not a function. What about E? It should be okay, right? I mean, you kind of question this a little bit, but nothing's straight up vertical. So if we draw a bunch of vertical lines, notice we're just crossing that graph just once. So that is a function. And then F is trying to trick you, and honestly, there's one point that makes the difference. Notice right here we're fine. Notice all these are fine. The only question is what's happening at -1? Well, since that is an open circle, we're not including it. And since that's a closed circle, we're including it. So at -1, it actually only has 1 y value, that y value up there. But the second I close that dot, what happens? -1 has 2 y values. That open dot is the only thing that's keeping it a function right now. Okay, so this is a function. But if we were to close that dot, -1 would have a +1 value and a -2 value, so it would not be considered a function. Alrighty, so now we're kind of jumping to how do we find domains if we're just giving an actual function. We're not giving an x and a y or an ordered pair, okay? So this is why we focus so much on that factoring, because we'll see it here, but we'll see it later on down the road. So it says when a function f whose inputs and outputs are real numbers is given by a formula, the domain is understood to be the set of all inputs for which the output is defined as a real number. That's really wordy, but it just basically means as long as you put the x in and one number comes out, you're good to go. But there's certain things like denominators and square roots where uh-ohs happen, little no-nos happen, okay? So it says when an input results in an output that is not defined as a real number, then we would say that function does not exist right there, and that wouldn't be part of the domain. So what are the 2 places we really need to worry about in this class is rational functions. Rational functions are just your big fractions, okay? Rational, the root word is ratio. So if you look down here, guys, at C and D, those are example of rational functions, because notice the fraction for both. Why are we worried about fractions? What can you never divide by? You can never divide by 0. So we never want the denominator to be 0. So basically we look and say, okay, it can be everything except for this number and this number, because it makes the denominator 0. Everything else is okay. The other things we want to do is radical functions. Remember, radicals are just roots. And we don't want it to be negative under the even. Okay, so we'll talk about that a little bit later in chapter 1, but odds are okay, because you can take the odd root of a negative. the cube root of negative 8 is negative 2. That's fine. But if that's a square root, eek, that has to be positive. So we have to kind of talk about what we do there. All right? So let's look at this first example. Does anybody know what graph f of x equals 2x plus 3 is? That would be just a what? What's mx plus b represent? Just a line, right? If we were to graph this as a line, but the slope would come into play because that's m, and b would be the y-intercept. We're going to talk about that here in a second when we do 1.3. So this is just a line. So just physically look in your head. When you draw a line, what do you put on both the bottom and the top? You put arrows. What do those arrows mean? It keeps going, right? So we're going to go to the left forever, and we're going to go to the right forever. So really the domain is everything, or all real numbers. How can you know that with here? I just asked you, can I put a positive or negative in for that x? Sure. Can I put a 0 in for that x? Yeah, 2x times 0, 2 times 0 is 0 plus 3, right? There's no number that's like, oh, don't put it in. We could put big numbers, small numbers, positive, negative. It does not matter. So this is no matter, I'll put it in words. Let's say no matter what x is, dot, 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 f of x will always be a real number. Meaning it doesn't matter if I put in a positive, a negative, large, small, I will just do the math. I'll double my x and add 3, right? That's all I'm doing. So what's that mean as far as domain goes? We do the whole number line. So think about when we were doing interval notation, guys. What's the furthest left we can go? How do you show forever to the left? Negative infinity, right? And how do you show forever in the right? Positive infinity. Do we ever hit either one? Nope, so we need parentheses. So this is a way to show all real numbers, or the whole number line. This is the domain they're looking for, okay? So that just means every single value of x is okay. All right, let's look at f of x here. Part B, he's the exact same idea, because I just talked about it. We can take cube roots of negative numbers. The cube root of negative 8 is negative 2. The cube root of positive 8 is positive 2. So if we have an odd root, we can have a positive or negative or a 0. What's the cube root of 0? 0. So this is the same instance. It doesn't matter what we put in for x. We'll take the cube root of it, and out will pop an everyday real life number. So again, this is an instance of negative infinity to positive infinity. All right. What if, I'm going to just go off to the side here. What if it was f of x equals the square root of x minus 2? Where was an even root there? What can't we take the square root of? What type of numbers? Negatives. And it's been a while. That was like the first week of class we were together. You can't take the square root of negative 4 because there's not one number when multiplied by itself gets you to negative 4, right? 2 times 2 is 4. Negative 2 times negative 2 is 4. There's no way to get that negative 4. So what we want to do is we always want this to be greater than or equal to 0. So you set the inside x minus 2 greater than or equal to 0. Okay? And you solve inequalities just like equation signs unless you have to divide or multiply by a negative. But this is just adding 2 over. So x is greater than or equal to 2. What does that mean? It means as long as we put an x value that's 2 or bigger, once we subtract 2, it always gives us a positive number, right? What happens if we put 2 in there? What's 2 minus 2? 0. What's the square root of 0? 0. What happens if we put 6 in there? 6 minus 2 is 4. The square root of 4 is 2, right? But what if I put negative 5 in there? What's negative 5 minus 2? Can you take the square root of negative 7? No. So this is kind of the cutoff. It needs to be 2 or bigger. So how do we write this in interval notation? Again, you'll see why we had that whole section last week. How do you write x has to be greater than 2 in interval notation? What's the smallest x can be? 2, right? X has to be greater than or equal to 2. So the smallest it can be is 2. Can 2 be included?
Yes.
Yes. So we're going to have a bracket. And then how do you show I'm going off to the positive direction forever? Infinity. So notice the difference there, guys. Odd powers will always be negative infinity to infinity because you can take cube roots and fifth roots of negative numbers. Even powers, we always have to take something greater than 0. So we're going to always have kind of this lower bound off to infinity or vice versa. All right, these next two are kind of why we were focusing on the factoring. What do we know that we never want to have on the bottom is 0. So I say, let's be little sneaky detectives and solve for 0, and then say x cannot be this, okay? So let's take our denominator and set it equal to 0. X minus 3 cannot be 0 is basically what we're solving. We're solving for what x's are not good. So the only difference I do is I put a not equal instead of an equal. But you solve them the same, right? What are we going to do to solve for x here, guys? Add 3 over. So what did we just find? We found out that as long as x is not 3, we're okay, right? Because what happens if x was 3? What happens when you put 3 in there? What's 3 minus 3? 0. But it's 1 divided by 0. We don't want that, right? But what if I put like 4 in there? What's 4 minus 3? 1. That's fine, right? What if I put 2 in there? What's 2 minus 3? Negative 1. And we can divide by negative 1, right? So as long as our x's are not 3, we're okay. So every other number but 3 is okay. 2 ways to show that, okay? One is called set notation. How they do it is they do squiggly bracket, and they say x, and then they do this vertical bar. This vertical bar means such that, okay? So this just means all x's such that x is not 3, okay? So that's called set notation. It's the set of all values that work. All x's such that x is not 3. Or they do interval notation, kind of like what we did last week in our co-requisite class. So is negative infinity okay? Is negative a million okay? Is negative 100 okay? Yeah. So we're going to start at negative infinity, and we're going to work our way all the way up the negative number line. We're going to hit negative 1, 0, 1, 2. All those are okay, except for where do we have to stop at? 3. But can we include 3? No. So what do we need? Parentheses. Okay? So this is a way to show all numbers less than 3, right? 2.99999 all the way to negative infinity. But what else do we have to consider?
Greater than
all the numbers greater than 3, right? So this is where, keep a space here just for a second. Keep a space. And then how do we show all numbers greater than 3 but we don't include 3? Parentheses to infinity. Does that look okay? So on our thing last week, do you remember how we show this set and this set? What symbol was in the middle? It was called that union symbol, okay? The union symbol is just an operational symbol meaning addition, but you only use the addition sign when you're adding two numbers like 2 plus 3. You use this union symbol when you're adding sets of numbers, negative infinity to 3 and 3 to infinity. This is basically how I kind of like, it's cheesy, but I say act like you're walking the number line, negative infinity, negative million, negative 100, negative 10, you know what I mean? And then you get to 3 and you're like, oh, there's a hole. You step over it. So this is you stepping over that hole at 3. Yes, sir?
Could you write it as an inequality?
Yes. And so how would we do that? We'd say x values less than 3 or x values greater than 3. Right? You'd have to be two inequalities, because if you do it in between, you're saying all the values between negative 3 and 3, right? So there's a bunch of different ways you can do it. MyMathLab, typically, for some reason, Gavin, we don't do the inequalities as much. We usually either do, this is called interval notation, or we do the set notation up here. Okay? So, D. What's different about D is we're going to do the same thing. We're going to take that denominator and say it can't equal 0. So take your denominator and say it can't equal 0. But this is what we were doing last week. We know how to solve linear equations like we did in C. You just always get that variable by itself by doing the opposite operation. Remember how we solved quadratics, a squared plus bx plus c, is using the AC method and getting it down to factors, and then we set our factors equal to 0, okay? So this is why I kind of was drilling that AC method, and we're going to finish today doing this worksheet, and we'll do that worksheet that we didn't quite finish last time. So our A is 1, our C is negative 3, so our AC is negative 3, okay? So we need to think of factors of negative 3 that add up to positive 2. Well, 3 is a prime number, so it only splits up one way, 1 and 3, correct? So which one needs to be positive, which one needs to be negative in order to add to a positive 2? The 3 is positive, okay? So I'm going to write it that way. X squared plus 3x minus 1x minus 3 cannot equal 0. And I'm using that cannot because I want to stress we're finding the things that make the denominator 0, which we don't want, okay? We'll do factor by grouping. What can we take out of the first two terms? An x, and we'll be left with what?
1x plus 3.
Beautiful. And then notice back here we have 1x and a 3, but the signs are opposite, so what are we going to factor out? A negative 1. I know that seems weird, but we want the numbers to stay as is. We want to keep it an x, we want to keep it as 3, but we want to switch those signs. So we're going to factor out a negative 1. So negative 1 divided by negative 1 gives you a positive x. Negative 3 divided by negative 1 gives you a positive 3. And right there you guys should see that our x plus 3 factor is shared, okay? So we're going to factor that to the top or the front, and what are we left with for our second factor?
X minus 1.
Perfect. All right. So remember, once you got it in factored form, again, we'll do this worksheet. I think I handed it out, but I just said don't worry about doing it. Once you get it into factored form, you just set each of those factors equal to 0, okay? So we're going to set each of these factors not equal to 0. We're going to put the not equal sign, okay? So x plus 3 can't be 0, and x minus 1 cannot be 0. Meaning, what are the two no-nos? X cannot be negative 3, and x can't be positive 1. What does that mean? It means if we were to plug either negative 3 or 1 into that denominator, we would do the math and we would get 0, which is what we don't want. We want every other number, positive, negative, big or small, that's fine, but we don't ever want 0 in our denominator. So, how do you write this? Well, again, my math lab's kind of pushing two ways. We can do it in set notation, okay? So set notation would just be x such that x does not equal negative 3 or 1. They just put a comma in between the two, okay? X such that x does not equal negative 3 or 1. Or they do interval notation starting at negative infinity, but then you jump over 2 holes, right? Here we just had 1 hole at 3 where we kind of just took a step over. This one, we're going to go up the number line, we're going to jump over negative 3, keep going from negative 3 on to 1, but then we're going to jump over 1. So let's see how that happens, okay? So I'm going to put a big or because I don't know which one my math lab's going to give you. So this will be negative infinity, go up the negative number line until you get to negative 3, stop, we don't want it, so put a parenthesis there, jump over negative 3 and start at negative 3 again, keep walking, negative 2, negative 1, 0, that's fine, till we get to 1, and then step over 1. And don't you agree that anything higher than 1 is fine? So we do 1 to infinity. Look how ugly that is. So however many no-nos, like however many holes you have, that's how many union symbols you should have, because your union symbol represents stepping over, okay? So this means all the negatives between negative 3 and negative infinity are fine. All the numbers between negative 3 and 1 are fine. And all the values 1 and bigger are fine. But we can't include negative 3, we can't include 1. So we're putting parentheses there and stepping over them. All right, so last thing here is how can we come up with domain or range by looking at the graph? To me, it's a little bit easier because you physically get a look at it and say, what x values am I covering? And you physically get a look at it and say, what y values am I covering? It's important to use interval notation, so we're going to use parentheses when things are not included, brackets when they are, and so forth, okay? So domain is always left to right, so left to right. And then range is always, I don't know how to say this, low to high? I don't know how, left to right. So low to high, okay? So either way, whether you're working with a domain or range, just think the lowest number to the highest number, okay?
Bottom to top.
Bottom to top, does that work? I know, I'm like trying to think of the words. Bottom to top. Because really low to high works for both if you think about it, right? Low x's to high x's, low y's to high y's, all right? So let's look at the domain. So we're going to do it in interval notation. Notice our function is the square root of x plus 4. So there is a restriction. We can't plug everything in because